If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay students, welcome you to the lecture 4 of this complex number series. So this is the last portion of that theory. So we have discussed until now some of the properties of Cauchy integral formula and theorem. So we will be continuing that one with singular points, and the last that is very important theorem, Cauchy residue theorem, how to calculate residues. Okay, then with this we will be concluding our theory discussion. From next class we will be starting numericals. Okay, then let's start discussing this portion. So what is next? Cauchy integral formula. This was theorem, now this is Cauchy integral formula. Cauchy integral formula said if your fz becomes analytic and you think about this integration, fz by z minus a. If fz is analytic, there is no problem. Now if you put a, it becomes problematic. So you think of a c contour that was on the contour c, the integration has to be done. Now there is a problematic point at a, so I take a circle around it. So entire area I know answer will be 0, so I will be concentrating on here only. That's I know. Okay, now how I will concentrate? I will shrink the circle as I will make r very 0. This was arm I. Next I will zoom. I will again go inside that r. Means I will be reducing the radius. Suppose this is my r. This was my r. Next time what I will do? I will keep it more small, little more r. That's why with this we will come to the end, only that point a. So you come a very tiny small place a. Very small. So you can remember this one in this way. It is not the actual thing, but I am giving you an understanding to remember. So if I come to this place, so what will left? Normal integration means you can think as a layman, you can think it is the area. It is the area. So if you are reducing r, so ultimately there will be no area left. You will only come with this circumference only. You can think of this circumference only, because inside there is nothing, because you are keeping it 0, 0, 0, 0. You are making r very small, very small, very small. So nothing is left here. So only thing left is the circumference. So you can think of all that way. And that circumference also imaginary circumference, because your r becomes very negligible, very 0. So what is the formula for circumference? 2 pi r. So 2 pi I, because it is imaginary, you can think of all that way. And what is left with f of a? What is the value of that function? Because you are thinking about outsides, because you give a boundary here, you are thinking about just here, then you give boundary, then you come close. So ultimately if you are coming very close and you are reaching a, then you will get f of a, because you are taking the value of z as a plus r e to the power I theta. A, then some circle, some radius you have taken, you have started from that point. Now because you are making it towards 0, so your z is coming towards a, because you are going inside that. So you can think of that way. So 2 pi r, radius is gone. Instead of radius, the thing that is left is a, f of a, which is also known as residue, or some sort of residue also. You will see that if I shrink the circle so much, so what is the thing I am left with? So I left with only this one. So you can remember it in this nice way. So we are making a circle around a. So if I am sinking the circle, the area is reducing. So ultimately I will get the circumference only. So some sort of 2 pi r, 2 pi, and r becomes negligible here, because it is imaginary. Everything is imaginary. You can think that's why I came. And the thing I left it is fa. So r is replaced by fa. That's the layman idea. Just to remember this one. Now if there is a z minus, it was power was 1. If it is n, then 2 pi I, then you have to take f n minus 1 means differentiation of n minus 1 at time, then you put a divided by n minus 1. F to the power n minus 1 is differentiation. This symbol is differentiation of n minus 1 times. That's it. So again you can remember this one, but the simple things are coming, so we will be using that one. That becomes very easy. What at the now? You have to remember some things which are known as singular points. The point at which it is not analytic, the function are no more becomes analytic. These are known as singular points, critical points. That means you can think the points where the continuity breaks, where it is not differentiable. These are known as singular points. So you can recall now what is you can correlate it to the normal algebra. Let us come to that. Suppose what is now isolated singularity? So again, a name, for namesake you have to remember what is isolated. Suppose that in the question it comes, you should not get confused. Suppose z equal to a is an isolated singularity. If there is no other singularity within a small circle around z equal to a. These are all mathematical statements. What is the main thing they are talking about? If I take an example, so here z minus 2, it is not, you can see if you put z equal to 2, then it becomes discontinuous. So it is not defined, it is not analytical at z equal to 2. So z equal to 2 is a singularity. Why it is isolated? Because around 2, only at 2 it is singular. 2.00001 you can put 2.00000. So these are mathematical expression as close as you can go to 2, but you cannot put 2. So these are known as isolated singularities. So mostly we will be dealing with isolated singularities only. So next, what is pole? What is pole? Pole you have already seen in control. So pole, a pole of order m, isosceles singularity of z is known as order m. If it is the highest power of 1 by z is m. So if you see it fz, this is a function. So 1 is also a pole, 3 is also a pole. If you put 1, then also problem occurs if you put 3. So z equal to 1, it is order 1 because power is 1. Z equal to 3, it is a pole, but it is a order of 2. Now there is one more name you have to remember. You can remember your holomorphic function, holomorphic, where it was analytic everywhere. Now it was analytic everywhere, but there are some finite poles, except some finite, some holes are there inside where it is not analytic. These are the holes. Then this is known as meromorphic function. Just to remember this. Suppose if it comes, you should not get confused what is meromorphic, what is holomorphic. Now what is residue? I was talking about residue while we were shrinking that circle. The same idea here. Suppose it is a fz of z equal to a. It is a pole at z equal to a. So what we will do? We will try to find the value of fz, but we will take out that pole. If I am multiplying, if my fz has a pole of 1 by suppose z minus a. So if I multiply with z minus a, what will z minus will get cancelled. Only thing is left will the without that pole whatever is there. Suppose there were z plus 2. So it will remain there. So we will find the value neglecting that pole. So you can think this one also, that differentiation Cauchy integral theorem, this one. Here you can say fz is without this pole. Without this pole, this was fz. So fa was directly I have written. So they have not considered including this one was fz. Now here everything total is fz. So you have to multiply with z minus s so that it gone. So that the only thing remains is fz. So here you can see. If you multiply with z minus a, that pole will get cancelled and the thing will left with this. So this is known as residue, the thing we are left with. Suppose if it is a pole of order m, then what will be the residue? We will see all this in numerical. Numerical becomes very easy. So 1 by m minus 1 factorial, limit z tends to a, differentiation 1 time less. And if you multiply with z minus a to the power m, that pole will get cancelled. The less things will left with. So you will left with this residue. So the last theorem that says what the calculating residue, this is the final theorem. Ultimately we will be using this theorem only for integration of any contour or everything. In maximum questions, in majority questions, you will be seeing this one, the last one. So this is known as Cauchy residue theorem. So if it says, if it is analytic in every closed curve C, except some finite number of singular points, there are points where it is not analytic. Those are the poles. So what will be the integration? Integration will be 2 pi and the thing you are left with. 2 pi I, you can think of that circle, you are shrinking that circle. So ultimately you will left with the circumference 2 pi I, and instead of r what it will come? What is the residue? Residue for all the poles who are inside C. Poles may be outside also, but they can suppose there are poles here, 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 but they asked you to see only in this zone, so you will be thinking only this pole only, not other poles. So some of the residues of poles inside that contour, over what region they are asked to integrate. One thing you have to be very careful, these formulas, whenever it is derived, wherever it is mentioned in all the formulas, integration's direction is always considered anti-clockwise direction around C. Around that contour, you always move in anti-clockwise direction. Suppose if you move in clockwise direction, some question they give intentionally in clockwise direction, then there will be a minus sign. Okay, I think that's all for complex number. We will start solving complex number questions in next class. You see, when we start question, it becomes very easy for us to understand. We will take reference of these classes also. If you like the video, then press the like button and please give your valuable comments in the comment section.